Hello and welcome to the new session of construction of character table for point group C3v. I am again Saurabh and we'll be looking forward for the construction of character table for this point group. How should we do it with the principal components of great orthogonality theorem? So the first we are going to consider about the elements of the point group C3v, and the elements are, as we know, identity C31, C32, sigma v, sigma v dash, and sigma v double dash, or sigma v1, sigma v2, and sigma v3 respectively. Taking ammonia molecule as a classical example, we'll try to get this concept done. Ammonia is a pyramidal molecule belonging to this point group, and we have learned in earlier video that actually the C31 and C32 belongs to one class, and three vertical planes have separate classes. So they belong to all of the three belong to one class. So we have three classes. You have one identity, C3, and a three vertical planes make one class. So let's do our job. First, write the point group of the molecule, write the symmetry elements in their classes, and then just decide what we're going to do about the number of irreducible representations. You must recall the fact that number of irreducible representation are equal to the number of classes. That was rule 5 in our the properties of irreducible representation. So we can now decide that because there are three classes, there should be three irreducible representations. Let them be tau 1, tau 2, tau 3, and let the dimensions be L1, L2, and L3. Now the question is, how should we find the dimension? But the rule says that the sum of the squares of the dimensions is also equal to the order of group. Now there are a total of 6 elements, symmetry elements in operation present in this particular point group. So how to satisfy L1, L2, L3, the squares and their additions to yield 6? Just think, and you will conclude that if we put two of them as plus ones and the third one as 2, then 1 square plus 1 square plus 2 square would be equal to 6. So let's do it. L1 equal to L2 equal to 1 and L3 equal to 2. If we do it, we find that possibly that the addition calls to be 6. Clearly, the two irreducible representations have one dimension, and the third irreducible representation has two dimensions. That means the matrix order would be 1 and 2 respectively for these representations. Now the rest of the things can be put into our basic frame, and that is something like this. You write the first row that constitute the point group. Then you have identity, 2C3, C sigma v, the three classes that have been shown. And now I am replacing tau 1, tau 2, and tau 3 by the terms A1, A2, and E respectively. Now why? Why A1, A2, and E? A1 and A2, they are actually the notations for one-dimensional irreducible representation, and E is a notation for two-dimensional irreducible representation. Remember, this E is not the representation for identity. In fact, it is only irreducible representation for that particular point group. It has a two-dimension. This is a two-dimension matrix. This is one dimension, and this is one dimension matrix. So, well, now the next is how to fill the characters of identity. Because A1 is one-dimensional, identity character should be 1. A2 is also one-dimensional, its identity character should be 1. But E is a two-dimensional. That means its matrix should be 1, 0, and 0, 1 type, and the diagonal sum would fall to 2. So this becomes 2. So it's quite easy to assign the characters of identity depending upon the nature of irreducible representation. So this row is now 1, 1, and 2. So simple, isn't it? Next, we should move to find the characters of the row. How can we do it? Now that states that summation of the squares of the characters is also equal to H. Now just look at this. Chi E1 E square plus 2 chi C3 square plus 3 chi sigma v square should be equal to 6. Why this? Because identity is 1, C3 is one class that has two elements, sigma v has three class that has three elements, and this is some equation that is something like this: 1 square plus 2 into 1 square plus 3 into 1 square, and that makes it 6. It simply implies that the characters of identity C3 and sigma v should be respectively 1, 1, and 1. So that makes the row like this. So 1 and 1. Now the question is to fill this vacant area. How to fill them up? And let's assume that they're x and y respectively. Once we assume that, we know that A2 and A1 should be orthogonal to each other according to the concept of the great orthogonality theorem. And if we are using the great orthogonality theorem concept, I will say that C 1 into 1 into 1 plus x into 1 into 2 plus y into 1 into 3, that should be equal to 0. Now, how should we place the value of x and y so that the total falls equal to 0? Quite easy. Just put x equal to 1 so that you get 1 plus 2, that is 3, and put y equal to minus 1 so that becomes minus 3. So 3 minus 3, that becomes 0. So it's quite simple to conclude that x and y should have plus 1 and minus 1 values. Let's put them there, and here we are successful in getting the values of x and y here. Incorporating in the A2 row, we have this. Now there is a question of finding the rest of the elements, rest of the characters, and that can be done by assuming the values like A and B. Let's assume that these values are A and B, and now to obtain them, we'll say that E must be orthogonal to A1 and E must be orthogonal to A2 also. So we must get two equations, they're simultaneous equations, and by solving them, we can get the value of A and B. So when you assign that E is orthogonal to A1, what we get is 2 into 1 into 1 plus A into 1 into 2 plus B into 1 into 3 should be equal to 0. Clearly, this equation is 2 plus 2A plus 3B equal to 0. If we go for another equation, we find that we get 2 plus A plus b into minus 1 into 3. As you just look at this table, you find that here, if I say E is orthogonal to A2, 2 into 1 into 1, A into 1 into 2, that's 2A, plus b into minus 1 into 3, that is minus 3b, and now that is possibly you have 2 plus 2a minus 3b equal to 0. So equation number 2 is, equation number 1 was 2 plus 2a plus 3b equal to 0. Now if you solve the equation, we get the values that a equal to minus 1 and b is equal to 0. So now we have something like this. We have the values of characters of A1, A2, and now we can determine the characters of E irreducible representation. That is, for C3, it is minus 1, and for sigma V, it is 0. So that makes the table complete, the character table complete. However, as you know, a complete character table also have some basis factors like translationary x, y, z, and the rotation x, r, x, r, y, r, z terms are there, and the binary products are also there demonstrated in the character table. These concepts that we will understand in later videos. So the important part of collecting characters for different irreducible representation is done here. Now we have asked a question that why we are using the terms A1 and A2, not A and B. Because, you know, B has to be antisymmetric with respect to rotation. But here we find that for rotation, the characters are positive ones. So instead of writing A, B, I'm writing A1 and A2 so that it can be justified that the characters are positive for the principal axis. Thanks for watching this video. See you in the next session.